It's time for our final video for this week. Today we're going to talk about control. If you remember, we wanted to enable our robot with the ability to autonomously navigate. Given some desired state, we wanted the robot to get there. We wanted the actual state of the robot to match our desired state. And we spent the last couple of videos talking about how we could estimate that current state using sensors. Today we're going to talk about, once we've got that state estimate and our desired state, how we would control the robot, or how fast should we spin the props so that we get to where we want to go. Now the robot, something like this, you can see this is an old E80 robot, is an underwater robot, and we're really only going to talk today about the horizontal positioning of the robot, not about the vertical. So the horizontal positioning is going to have two thrusters placed in the horizontal frame, maybe like this. Here's a top-down view. So here's our problem. We've got a desired XY point, we've got a current estimated XY position and maybe orientation of the robot, and we want to get to that desired point. How are we going to track it? Well, we're going to have to figure out how to spin these little propellers, because when we spin these propellers, they're going to generate a force, one from the right motor and one from the left motor. Now these forces are functions of the output of our controller. We're going to call these UR and UL. These are signals that our controller are going to spit out. And we're going to note that the size of the force output from this motor is obviously going to be a function of the control signal that we send to it. One final thing we'll note is that there's a difference of 2L between these motors, or 1L from the center point of the robot to the motor. We're going to need that for geometry. So to recap, what we want to do is pick the control signals we send to the robots, UR and UL, so that we can move to some desired XY position. Our strategy is going to always point the robot towards that XY position that we want to move to. And we're going to drive in the forward direction at some nominal speed to that point. So how are we going to set this up? We're going to start with a dynamic model, and we're going to look at the rotation of the robot. Because we're always looking at pointing the robot toward the goal point, we're only really going to worry about the rotational model of the robot, where the robot's pointing. So we've got a moment of inertia times our rotational acceleration. It's going to be some function of drag and the input torque. Now in this case, you've got this higher order drag term. We're going to say at low speeds we can drop this drag term. We're also going to change our variable name just to make it a bit more intuitive, so that we understand that this is rotational yaw angle acceleration and this is yaw angle velocity. So we've got the moment of inertia times our rotational accelerations approximated as this negative drag term that's going to impede our rotation, plus our input torque, N, or isolating our rotational acceleration this way. Now the input torque N is a function of the two forces, one from each thruster, the right and left thrusters, that is. In fact, now we need that distance L from the center point of rotation, and we can say that the input torque N is L times the output force from the right thruster minus L times the output force from the left thruster. You can draw this out, and probably should if you don't understand where this comes from. Now, each output force from the thrusters is some function of the signal coming from the controller. We're going to approximate that with a linear function, maybe with some constant c. And this you should probably do some system identification, or maybe you've already done something like this way back in E79. We're also going to do this for the left thruster, and that is our right control signal is a combination of a nominal forward signal and some signal that we're going to calculate at every time step. Similarly for the left motor. Now just to note, we're going to set these as constants, and they're going to get us some forward motion. These terms, which we're going to be set to be the output of a controller, a feedback controller, are going to be the parts that actually get us steering in the right direction. So let's substitute those two control signals into our input torque equation. And what you'll notice is that the UNOM terms cancel out because of the negative sign, and we're left with 2LCU. So these are constants, which we determined ahead of time, and now our input torque is really a function of this U. So the question is, what should U be? It's the output of our controller. Well, we're going to start with a simple proportional feedback, which basically sets the U to be some proportional gain times the difference of our desired angle and our current measured angle. And I guess we should probably set the desired angle to be pointing towards the goal point. Seems like it would make sense. That's been our strategy. We can then plug U in, and we now have an equation for our input torque that's a function of our desired orientation and our measured or estimated orientation. The rest of these are constants. Now we can take N, plug it into our dynamic equation right here, and we can start to produce what looks like a second ordered equation. It might even be a second order LTI equation, similar to those that you've seen in E79, where we've got an input signal and an output signal, theta. Just in case you don't remember what such an equation looks like, I've taken all the constants and reparameterized it into A, B, and C for you. Now this might look much more familiar. It's a second order system, and with it comes all the characteristics of a second order system that we learned about in E79. For example, transient response. So such a signal might have a desired theta, the blue of 1 radian, and depending on our values of k and j, etc., you might get an underdamped response, overdamped response, which I haven't shown. But again, it's the same thing as in 79. This response is going to be determined both by the physical parameters as well as by our control gains that we can actually choose. So to be clear, choosing our gain Kp is important because it'll affect omega n as well as the stability of this system. So to summarize, we can set our control signals this way for each thruster, and we will get the second order transient response to actually track the desired angle towards our goal point. So we went through some math and things like that, but really all you need to know is you can set your control signals to your right and left thrusters to be in this format. Some nominal control signal to achieve forward motion, plus an extra term to get the robot pointing towards the goal. If you implement this in your robot, you will effectively get autonomous robot navigation. The robot will move to any XY desired position in the ocean. Pretty cool. To summarize this set of videos, closed loop control is going to be necessary for our waypoint navigation. All that modeling, design, transient response analysis, and control theory that you learned in E79 is going to be very, very useful here, assuming that our system is LTI. And you probably remember we made some assumptions to put it into an LTI format. These will not always hold, so beware. Finally, something we haven't talked about so much, but you should be aware of, the controller performance is going to be definitely limited by the performance of the state estimator. For example, if you have a really bad measurement of theta, then obviously your theta controller is not going to do well. Good luck and have fun in this last lab. It's one of my favorites.